So, hello and welcome to the Power Electronics class. Um, for those who already know me, my name is Behnam Askarian, and this semester I will be teaching Power Electronics. My email is baskarian@wtemu.edu, and my office is in 221J. Um, for this class, um, we don't have any required textbooks. I will provide you with all the necessary materials. If you have already had classes with me, you're familiar with the materials that I provide and how it's going. But this semester, we're going to have more homeworks and quiz compared to the previous semesters. And we also would have a final project as well. The recommended textbook is The Power Electronics by Nid Mohan, and it's on Wiley. Again, you don't need to get the book, but if you want to solve some extra homework problems, it's a good resource. I would also provide homeworks and extra examples if you need. And rather than that, you don't need anything else, maybe a simple calculator in the exam and on the exams. And in this course, we will cover everything that is a combination of electronics and power systems. So power electronics is basically a merger of electronics and power systems mainly, and it works on the electronic parts, the physics, the semiconductors, the controls part, the microprocessor and microcontroller part of power electronics, which are technically the electronics that we use in power systems. Now, you may think power system is high power. Not necessarily. Power electronics are only also used in low voltage, low power situations. And the basics of power electronics here that we mainly focus on are switching. Because with switching and with transistors, with switching, we can manipulate signals, AC and DC signals. So it's going to be mainly on semiconductors, diodes, power transistors, and power ICs and so on. Now, you're already familiar with the objectives of ABET. I'm not going to go through that. Just please read through them. And our main goal here, we would start with DC-DC analysis, then we go to DC to AC, AC to DC, and AC to AC analysis. We would study choppers. We would study buck and boost converters. We would study AC to AC converters and inverters and so on. Now, for this course, the evaluation is as follows. Attendance, which are quiz that I randomly may take, is going to be 5%. The final project, as I mentioned, is going to be 10%. This semester, we're going to have a final project, which at the end of semester, it's going to be a buck or boost converter or a DC to AC inverter, depending on what you prefer. But it's going to be an individual project. It's not going to be a group project, and each student should be able to design and build the inverter or a converter that they desire. But no two students should have the same project as well. So it's going to be before we, at the end of the semester, 1 or 2 months before that, I will give you a list of projects, or you can come up with your project and we can pick from that. So no two students have the same project. We're going to have 2 midterms. Each midterm is going to be around, it's going to be 20%, so 40% on midterms, and homework assignments and quiz, which it's mainly homework. It's going to be 15%. By the way, the attendance for online students, each day or each week that I post the videos, there's going to be a quiz. They have 1 week to take the quiz, and that's going to be their attendance. And for you, it's going to be in-person quiz. And the final exam is going to be 30%. And the grading, again, 90 to 100% is going to be A, B is 80 to 90, C is 70 to 80, D is 60 to 70, and below 60 is F. And I believe if you get a D, you have to repeat this class. And one important thing is about homeworks. Well, once I post the homework, you have 10 days to submit your work. And after that, unless it's emergency, family emergency or something like that, I would not accept late homework. And final exam is going to be a comprehensive exam. It's going to cover the whole all of the materials that we covered in the class. So one thing that I would highly recommend is try to do your best on your homework and on your homeworks and your midterms, because I see a lot of students, doing not so well on the midterms and trying to compensate for on the finals, but the final is going to be much more difficult in any level. It's going to be comprehensive, a lot of more materials, and the questions are usually more difficult as well. So try to do your best on your midterms. And again, attendance policy, if you miss more than 3 classes, then I would start deducting. Great. Again, attendance also is connected to your quiz as well. So if you miss the quiz, you're going to miss those points as well. Now, I already mentioned about homeworks. It doesn't need to be an engineering paper or something. I just want a clear scan and in PDF format of your homework. And for one very important part, I'm going to just skip the integrity part, but the AI part is very important. Last semester, we had a policy that you cannot use AI at all. Obviously, that's not realistic. So we have changed that a little bit. You can use AI as long as it is permitted. By mean permitted is that anything that is related to your learning. If you don't understand a question that I solved, or if you want to learn more about a subject, obviously you can use AI or any other tool while it's for learning. But any use of AI on your assignments, homework, quiz, and the exam, obviously it's forbidden. And if a student has been caught using AI in any of those exams, especially I see some of that for the online students. Obviously, in-person students, you can't use AI during your exam because it's a written exam and you're present here. But if they use AI in any mean, it's an automatic fail. So be careful where you're going to use AI. Again, for learning, it's completely normal. If you want to even help you on your project, you can use Flux AI for building your PCB for your final project or any other mean. But for turning in assignments and also for your exams, it's not acceptable. And my personal experience is when you use too much of it, it makes your brain lazy a little bit. Here, I don't want you to memorize all the formulas, equations. You're going to forget it next semester or 2 semesters from now. When you go to, find a job, you're not going to remember an equation that I gave you about NP junction, diodes or something. But what sticks with you is the problem solving and the understanding of the concept of the material. That's the important part. How does a buck converter work? How does a boost converter work? What is an inverter? What is a converter? What is the difference even? I see a lot of people don't even know the difference between them. So I want you to learn critical thinking and be able to have a problem-solving mindset. It's very important for engineering student. So try to solve the problems on your own, even if you fail, if you have to try 2-3 hours on a question. Believe me, if you try 2 hours on the first one, next one would take maybe 5-10 minutes. And don't try to memorize the equations. Try to solve them step by step. So again, generative AI is completely prohibited for exams and assignments and so on. So please read through the uh, ADA statements and so on, um, and the safety statements as well. Now, the tentative calendar for this semester, this week we're going to start with Introduction to Power Electronics. We're going to go through what is actually power electronics, the definition of power electronics, different types, and so on. Second week is going to be semiconductor devices and switch losses. Uh, silicon diodes, germanium, NPN junctions, and so on. You are familiar with a little bit of that in electronics. And week 3 is going to be switch mode, DC to DC converter, switching analysis, topology, selection, and design. And week 4 is going to be discontinuous conduction mode. Week 5 is going to be designing feedback controllers in switch mode DC power supplies. And week 6 is going to be the continuation of that. Week 7 is going to be review for exam 1 and exam 1. As you are familiar with my classes, we have a review session before each exam, and I highly recommend that you come to the review exams because um, a lot of problems on the exams, we solve a lot of problems that are similar to the problems that we have on the exams. Week 8 is going to be a study of AC to DC rectifiers. You are already familiar with rectifiers. You studied that in electronics, and here we want to go more into detail and solve more sophisticated rectifiers as well. Week 9 is going to be power factor correction. Week 10 is going to be magnetic circuit concepts. Week 11 is going to be isolated DC power supplies. And week 13 is going to be switch mode, DC AC inverters and their applications in UPS, motor drive, and power systems. Week 14 is going to be review for exam number 2 and exam number 2. Week 15 is Thanksgiving break. Week 16 is going to be utility applications of power electronics and review of a final exam. And week 17 is going to be the final exam. And yep, that's it for the syllabus. The syllabus is already on Canvas. Also on Canvas, you can find the material for the course. I've already uploaded them. The lectures, you can go and take a look at the lectures and the homeworks, but I'm gonna obviously, these are not available to take right now. And also there's a link to the course YouTube channel. So if you want to go back and revisit the course material, on the YouTube channel, I have the course material from last year, the recordings from last year, and I would add the recordings for this year each week that I record them as well. And the quiz would be also on Canvas each week. Please check your Canvas weekly because sometimes you don't see an announcement, but you're going to have a quiz pop up and you have a limited time to take the quiz. At any point during the course, if you have any questions, just please stop me. I will be happy to explain it again. Maybe your question would be your friend's question as well. And I'm very comfortable to, explain anything 100 times. And I'll be happy to do that. We don't have such a thing as a dumb question. Some questions, you may think it's a little, but they have a lot of points sometimes in them. So please stop me at any point and ask any questions that you have. I will be happy to answer your questions. Regarding emails, because I have, again, as I mentioned, we have maybe some classes I have are 50 online students. So I have a total of maybe 200 students or something like that in just 3 or 4 sections. So just give me some time to answer your emails. If it's a weekend, please wait until Monday. I would try to reply to your emails as soon as possible, but if not, just send me a reminder after a day, or because I get so many emails and sometimes it gets buried on. But you can call my office is there a more emergency, and also I already mentioned my office hours. My office hours are on Monday, Wednesdays, 10:15 to 11:35, and also Tuesday, Thursdays between 10 and 11. You can call me, email me, we can schedule an appointment, or you can just come to my office. I'm usually in my office at that time, Monday, Wednesday. After my class, I would be in my office till 2 p.m. usually. Just knock on the door, and if you have any questions, I'll be happy to help out. Is there any questions about the syllabus and the course? No. Okay. So let's start with today's class. So, introduction to power electronics. The outlines of today's class is going to be introduction and definition, some applications and examples, and design requirements. The agenda is going to be definition of power electronics. Sorry. Industry overview and market share analysis, multidisciplinary nature of the field, block diagrams of power electronic systems, the need for power electronics, types of power conversions, need for control, figures of material for power electronic converters, and also future trends. You can read faster than I can. This is my second language, so obviously I'm just going to explain. This is an interesting picture that I would like to share. Can you guess what's the largest man-made machine on Earth? Yes, our power grid is the largest man-made machine on Earth. In some sense, it's just a single machine. The grid in the US, like ERCOT in Texas that we have, is completely connected. And imagine thousands of miles of wires and transmission lines. You have power stations, power plants. You have transmission lines. You have distribution centers. And you have consumers. And a lot in between. Now, managing this is a tremendous task. And the way we do that is through control systems, computer softwares, and also power electronics. And I'll explain more. Now, you may ask, what is power electronics? And that's the importance of power electronics, that we can control this man-made machine. So, as you know, electronics is a solid-state electronics device, and they're driving circuits. Examples are, as you know, transistors and diodes that we use, and amplifiers and so on. Now, power, the definition is the static and dynamic requirements for generation, conversion, and transmission of power. And control is the steady state and dynamic stability of the closed loop system. And the definition of power electronics is the application of solid state electronics of the control and conversion of power. Now, a power electronic circuit is mainly used to convert electric energy of some sort of supply. That could be DC, like a battery, it could be a solar panel, it could be an AC generator, to supply into a voltage or current, which is usually a different frequency or amplitude that is suitable for the user load. Now, this is a good graph image. We usually have a power input, the power processor, the power output, which is connected to the load. And a power electronic system usually has a feedback, which is connected to the controller, which controls the signal. So we have the feedback loop as well. And I'll explain the feedback loop actually is a very important part of this. Now, the input power could be AC or it could be DC. and the output could be AC or DC. So we can have an AC to DC converter, or an AC to AC, or a DC to DC, or a DC to AC. Now, how do we measure the input power? Voltage and current, depending if you have a DC or an AC power. If you have an AC power, then we have to also have other parameters to calculate power as well. Do you know what the parameters are for measuring AC power? What is an AC power? Apparent power. Yes. And it has two terms. S is a combination of, do you remember what it is? Real power and apparent. Apparent power is actually the power. So apparent power is going to be real power plus imaginary power or reactive power. Yes, this is just a reminder. Now, what is real power related to? VI cosine of phi. And what is imaginary power? Yes. So this is our real power, and this, as you mentioned, is our imaginary power or reactive power. Now, what is phi or theta? Yes, it's a phase angle. And what does it show? What is the phase angle between? Perfect. It's the shift between your voltage and your current. So if this is the voltage, the red, and the current is in blue, then we have the phase shift, and this is our phi. Now, AC, we have reactive power and real power. Which one do we want to maximize and which one do you want to minimize? Yes, we always like to maximize our real power, and we want to minimize our reactive power. Okay. Reactive power in motors, for example, anything that has a coil inductor, that creates loss, it creates heat, and it's not desirable. The real power is, well, transfers to, real work most of the times. So when we say power input, VI, depending on if it's AC or DC, it could be real power. All we are asking about the apparent power, but in DC, it's just VI. Now, during this process, we can increase or decrease the voltage. We can decrease or increase the current. So the power processor can increase or decrease the voltage, or it could increase or decrease the current, and I'll explain more about this. Or it could change the frequency. So we can change the frequency, we can change the voltage, we can change the current. We can even change the angle, phase, some cases. And that's how we match the input to the load. So for example, imagine we have an AC generator, a grid, which is our power input, the outlet, but our load is a DC motor. So what should we do? We have to convert the AC to DC. First thing that we have to do, we have to match their voltage. This is just an example and just a reminder as well. Let's do a realistic example. Imagine our input power is a single phase outlet at 120 volts, 60 hertz is our input. And we want to connect the load to a 12-volt DC motor, or to a charger to charge our phone. So first thing we need to do, we have to go from 120 volts to 12 volts. How do we do that? Perfect. A step-down transformer is a great idea. So we can do a 10-to-1 step-down transformer, and the voltage goes from 120 volt AC to 12 volt AC. But so we have an AC voltage. What is the next step? Perfect. Use a rectifier. And what does a rectifier do, as you remember from electronics? A rectifier converts AC converts AC to DC. And one famous rectifier that we can use is a bridge rectifier. I'm not going to add, we have to add a couple more components like a capacitor and an inductor to smooth out and reduce ripple factors. But this is an example of a simple power processor that converts AC to DC. Now, the voltage manipulation or changing part here is done by a transformer. A transformer is not technically a power electronic tool, but the power electronic tool or component of this that we have is our bridge rectifier, which are semiconductors. So we can say technically the bridge rectifier is our power electronics part. Now, this is a simple system without feedback, but in most systems, advanced ones that you want to have a steady voltage in the output, you also need a feedback. Let me give you an example. So if this is, turning a DC motor, and the DC motor is a servo motor or a step motor, and you want to keep the torque, if there's a load on the motor, once you apply the load on the motor, what happens is the voltage drops, and you're going to have changes in the voltage and the current. And that's not desirable. So what we do here is we usually have a feedback system that goes through a control system that would manipulate the input and output voltage. So there we can increase the voltage. Again, if it drops between 11, below 11, it will increase it again up to 10, 12. Those are for sophisticated systems, more expensive ones. But this one, a normal rectifier that you also, I think, built in the labs as well, that's a feed without a feedback system. It's a feed-forward system. And not a feed-forward, but it doesn't have any feedback. But some systems may have feedbacks, more sophisticated and expensive ones. Some ones don't need it. Some power electronic conversions require feedback, like when you have an inverter. Most times you need that. Some of them are like a rectifier, don't necessarily, or a buck or a boost converter. If it's a fixed output, you don't need it. But if you want to change the input and adjust that, then you definitely need that. Now, the measurement that we do here is we can measure voltage, current, or frequency. Okay, and I'll explain why we need to measure if we have an AC to AC converter, sometimes we don't want to change the voltage from the input or the output. We want to change the frequency. One example is, imagine we want to connect Europe to the US grid. It's a different frequency, so you definitely need a AC to AC converter to be able to match those frequencies, which is a very tremendous and difficult task, not that easy. So the measurement could measure the voltage. So here we could say it's 12 volts, and then we have a reference that says the voltage should be around, let's say, 12.2 volts. So the controller would bump it by 2.2. Imagine the reference voltage that we have is 12 volts, and then the measurement that we have is 11 volts. So it's going to boost the power processor to correct that voltage to up to 12 volts. So you can have a feedback or not, and this is depending on how sophisticated and advanced the system is. Now, as mentioned, power electronic deals with the conversion and control of electrical power using power semiconductor devices. that operate as high-speed electronic switches as well. Now, this is an interesting graph. It shows on the left you have electronics, on the right you have power engineering, and the combination of these two when they merge is power electronics. But again, some people get this wrong. You may think power engineering means very high power, high voltage. Power electronics could be from milliwatts up to gigawatts. So it's a wide range. Anything from, again, a few millivolts to megavolts, power electronic systems works. The thing is, it's a combination between mainly working with supply voltages and also the power engineering and also electronics as well. Now this is another interesting graph. It's a definition of power electronics. Again, it's a technology for converging one type of power to another and for processing it and controlling the voltage and current, sometimes frequency as well. So power in general. And it provides the basis for a variety of new electrical circuit architectures that allow substantial improvement in performance and flexibility. And you can see here we have electronic switching circuits. We have, which could be normal circuits that you have like diodes or transistors and so on, like a MOSFET transistor that is simply just to turn on and off a switch, like on a light or something, or a sensor or something. And then we have converters. Again, as we mentioned, we can have AC or DC input or AC and DC or DC output. So we have 4 possible converters. We have AC to DC, DC to AC, DC to DC, and AC to AC. And the objective is to convert the input and the output so they would match the required voltage and current. And they usually convert one type or level of a voltage or current waveform to another. So it can be like a high voltage to a low voltage or a low voltage to a high voltage and so on. Now you may ask, why do we have AC to AC converters? We have already studied, I don't know if you've studied AC to AC converters. Can you give me an example of AC to AC converter that you already learned? Perfect. Transformer is a perfect example. But transformer is not a power electronic device technically. Okay, so transformer converts AC to AC. Yes. But transformers can only change the voltage and the current. But in power electronics, what we mainly are focused on in AC to AC converter is frequency change, which transformers cannot do. Transformers can only convert, one level of voltage to another. So we have step down, step up. But in power electronics, you have to first convert AC actually to DC, then invert it back to AC. So it's a difficult task to do that. And finally, we have high current or voltage electronics as well, which are used in different applications like radars, communication systems, and so on. Now, the multidisciplinary nature of power electronics is that it's comprised of several disciplines. You have electronics, semiconductor devices, analog, digital circuits, control design, magnetics, physics. The physics part is very important. Electric machines, power system engineering, circuit simulations, communication and networking, and storage. So it's a combination of multidisciplinary. And a lot of advances that you see right now in robotics, renewable energy, communication systems, EVs, would not have been possible because of power electronics. 20, 30 years ago, we did have, actually electric cars are technically older than internal combustion. We first had electric cars and DC cars, then combustion engine. And mainly they were like acid, batteries with a DC motor, but they have a lot of limitations. With the rise of power electronics, a lot of that has been addressed. So we have a problem of battery and storage, but that's the main problem that we have. But a lot of problems like DC to AC converters, charging, fast charging, all of that is solved by power electronics. Most of that is solved by. Another example are drones. We wouldn't have drones without BLDC motors. You know what BLDC motors are? Brushless DC motors. Their power to weight ratio is extremely high, turn to weight ratio, and that's the reason they are easily able to lift multiple times their own weight. Now, BLDC is a type of, I can say, AC. It's a combination between AC and DC motor, and without power electronics, without having the switching and PWM and switching system, you cannot convert a DC battery to and be able to run a BLDC motor. So we won't have drones. A lot of these high efficiency EVs, because a lot of them also use BLDC motors as well. Newer EVs, they use AC motors, but the thing is, the battery is DC, so you need a power electronic unit or an inverter to convert that DC battery voltage to AC to run the motor. The reason that they use AC, asynchronous motors or synchronous, is because it's very efficient and it doesn't require maintenance. So the first cars, the reason it wasn't that much popular is because DC motors, they use commutators and those wear out, so you need maintenance. That's a big problem with them. And because you can't have very high voltage, you're going to have a lot of waste in the system, heat up. But with the power electronics now, new EV architecture is 1,000. They also have newer like cars. They have 1,000-volt architecture, but 200, 250 volts like Tesla ones is very normal right now. Even 800 volts, 400 and 800 volts architecture is very, very common. So the whole system works on 800 volts. And imagine controlling that system and running the motor is going to be a tremendous task. Another application of power electronics that has actually significantly, I would say, improved the efficiency is in renewable energy systems. So solar panels would not work, would be almost useless without inverters, because you need to convert that DC to AC. Now, a lot of companies are coming up with these solar panels that have micro inverters on them. So the inverter is attached to the solar panel itself, and you just put it in the sun and it produces 120 volts, 60 hertz. So the inverter, they call it micro inverter, and the panel are connected to each other. And if you build a solar farm, again, you need to be able to connect them, communicate with them, troubleshoot them. You need to have large inverters. That inverter needs to connect to the grid and synchronize with the grid. That's a tremendous task. We have off-grid and grid-tied connection systems. Those have completely different power electronic systems. A grid-tied needs to have a feedback loop to measure the frequency and the voltage and current and power from, and also the power factor, everything from the grid, and adjust the output to match the grid. If it doesn't do that, it's going to damage your power plant or system, and also the grid. It's very dangerous. And all of that is done through power electronics and control system. Another example is in wind turbines. Newer generation wind turbines are using permanent magnet generators. Again, they are using DC generators, but the output is AC, so you need a huge inverter. One other application is HVDC, which we call high voltage DC. It's for very long transmission lines, over 500 miles, or undersea cables. They convert AC to DC, and then they have to convert back DC to AC, so you need an inverter. The reason that they use that, because they want to eliminate reactive power and the loss that you have for the inductance and so on. So a lot of different tasks. Another task is going to be, that are using them a lot, is going to be communication systems, all these smartphones that you have, we have what we call a BTS, an antenna that all your phones connect to that, and those connect through a mesh system and a fiber optic underground cables. Now those antennas are very high power, and those are using power electronics. 10, 15, 20 years ago, that used to be the size of this, a trailer. Now they are the size of a suitcase because of power electronics. I'm old enough to remember these old chargers, DC chargers for phones. They used to be huge for a laptop. Now, with the help of power electronics, they made it the size of your thumb. So power electronics is helping in a lot of ways in reducing weight, and radars. They use power electronics all the time as well. And also medical equipment such as MRI, CT devices, and so on. Now, power electronics in terms of topical areas, we have the conversion technology, circuit theory, conversion efficiency, switching matrix, signal processing, EMI and filter circuits, magnetic components, and rotating machines. And then we have power controller technology, IC control packages, microcontrollers, microprocessors, digital and analog electronic circuits, control theory, transient and stability issues, digital and information signal processing, and simulation. And finally, we have power semiconductor technology like power devices, power ICs, derived circuits, protection circuits, and heat sinks. Now, this graph shows the interdisciplinary, characters and nature of power electronics that covers circuits from circuit theory to signal processing to electronics, magnetics, power systems, machines, solid state physics, simulations and computing, and so on. And I'll give you an example later on. A simple inverter, you need to have signal processing to be able to process the signal to minimize noise and harmonics for the output. So that's one part. You need to have a switching. So that switch requires solid state physics and power switches. That's a different component. Then you have to have a control system to be able to get a sample from the output and match the output with the input. So feedback loop systems. You need to have circuit theory. Need to know how you need to create the filters to if you need a high pass filter, a low pass filter, or a notch filter to be able to eliminate noise or unwanted noise and so on. You need to be able to design the circuit, so you need to have a simulating tool to run it before you build it. So it's a combination of all different fields of electronics and electrical engineering. So next section is the power electronics as an enabler of technology. It's an interface technology, physical and virtual. You can see we have a source, a load, and we want to be able to connect these source and loads with a converter. It's considered one of the most vibrant technology sectors due to ever-increasing applications in renewable energy, as I mentioned, computing, sensing, and communications, IoT, and because of its overlap with many other industry verticals, from interfacing a mobile phone battery, hybrid cars wheels, power plant power generation and distribution to a nuclear reactor, require efficient power handling from milliwatts to megawatts or gigawatts to facilitate the transfer and conditioning of power from the source to the load, and to be achieved with less cost, high energy efficiency, high power density, high reliability, and neatly. Now, this shows an interesting graph. Which you can see power electronic systems are all around us. They're all everywhere. By 2030, 80% of electricity could flow through power electronics at generation, storage, transmission, distribution, and end use. This shows an interesting picture of a power plant and the power converters in between transformers until it reaches the end consumer. Now, with the rise of the concept of microgrids and smart grids couldn't be done without power electronics. And in future, if you take smart grids, you would learn more about power electronics, the control systems. In a microgrid or a smart grid, the difference, by the way, between a smart grid and a normal grid, traditional grid, is that a traditional grid is a one-way system. You have a power plant and you have a consumer, and there's no communication between the power producer and the consumer. And for a power system, it's an on-demand system. You cannot store the power. So whatever is generated must be consumed at the same time. That's the reason they have very sophisticated modeling system to predict what time of the day and which day they need to increase the output or decrease the output of a power plant. But the good thing about a smart grid is it's a two-way communication system. So usually the house, they have a communication system. Like one example is when you have a smart thermostat. Do any of you have a smart thermostat at home? So a smart thermostat, if you have like a Google Nest or a Ecobee or something like that, that sometimes the power company like Exo, and they doing that actually in Montgomery County in Houston, they give you free smart, smart thermostats. But sometimes there's a catch, not all the time. The catch is that they will give you a smart thermostat and they'll give you some incentives, like they'll reduce your power bill as long as they have certain control on your thermostat. So what the power company does is during like peak hours, instead of ramping up, power production, which is very, very power generation, which is very expensive. Sometimes they have to, run a generator or something, which is very expensive. They will simply reduce the consumption. So they will put your thermostat instead of like 70, 68, 69, they will put it on 71, 72 for a few hours. So they will pass the peak. So it's a two-way connection. It's a microgrid is a sub category of smart grid. It's a smart grid inside a smart grid. And a microgrid is technically like a closed community. They have their own power, for example, but they could connect to the grid as well. So they will sell the excess power to the grid, and if they need power, they would buy it. But there's need to be a very delicate balance and a precise control system that works. It's incredibly fast. Even if you are not able to communicate in milliseconds, it's gonna, cause damage or disruption in the system. So now that power electronics are becoming more and more integrated in the systems, for example, in a solar farm, they are able to delicately balance between how much power they need to inject in the system, how much power is consumed, how much power is needed. And now with the rise of AI, they can actually project what the power consumption would be on July of 2028. At the certain day, they can do it with a good guesstimate. They could do that. They put a lot of data into it, like weather data, if there's a heat wave or something like that, and they could adjust their output and so on. But none of that could be done without power electronics, and the possibility to control all these input outputs in real time and to be able to communicate with them and control them. Yeah. Now, one example that you can see here is going to be fuel cell generation, wind generation, and also you can see PV and DC. So fuel cell, battery are going to be the future in renewable energy. And most of the capital and investment and technology and research is going through storage, because now the price of solar panel is actually cheaper than coal power plant. If you want to build a power plant right now, anywhere in the world, anywhere, solar farm is going to be cheaper than a coal power plant. The problem is that we have solar in the middle of the day that we don't need it that much, but a coal power plant could run 24/7. Solar, you can't obviously use it at night. So how can you mitigate that, solve that problem with storage? Now, storage could be different ways. They can use chemical like batteries. They can use hydro dams, that pump water to a higher elevation and then release the water at night and generate generate power. That's like 60-70% of stored energy in the US right now. And other technologies like fuel cell, a flywheel. There is a technology right now that they actually build these silos, they fill it with sand, and they run hot water or these hot elements. During the day, solar is going to heat it up. During the night, they run water through it and produce energy. Some systems, if they want to use it for cooling or heating, for example, during the day when there's a lot of solar, they would make a lot of ice. During the night, they would melt that ice to cool a building. They are using it right now in New York City. So different ways, but all of these again require power electronics for managing batteries. If you heard about BMS, battery management system, it's a delicate balance between how much you can deplete and how fast you can charge a battery. Without a BMS system, let me give you an example. First electric car mass-produced, technically, not the Chevy that came, that was not mass-produced, was Nissan Leaf. The Nissan Leaf, when it came out, 2005, 6, something like that, the claim range was 100 miles, 110. But quickly after 2-3 years, the range dropped to 20, 30 miles. Now, if you find a used one, it's like 10, 15 miles, something like that. The reason is not the chemistry. The chemistry stayed mostly the same. The problem was heat. The mistake that Nissan did with that car was it's an air-cooled battery, not a liquid-cooled battery. And an air-cooled battery, during hot days or when you charge it too fast, the battery gets too hot and it's going to degrade. The lifespan of the battery is significantly decreased. But now newer cars, because they have BMS system and they could control each battery to its smallest module. Like if you have like a 4086, battery, they can manage it down to there. So if there's a battery cell that it's, went bad or doesn't work, they can isolate that even. And they could control every single module and control its charge. For an optimal battery, the optimal charge should be between 20 and 80%. If you charge it over 80% or let it deplete under 20, it's going to significantly decrease its lifespan. Now, BMS systems are these control systems, power electronic systems, and these control systems that are able to manage and keep the battery in perfect, condition. So I'm just going to, give you an example. 15, 20 years ago when Nissan Leaf came out, the battery span life was 3 to 5 years. Now, all the manufacturers they provide warranty for the batteries for at least 8 to 10 years. We don't have long-term data, but there are Teslas that are running for 1 million miles, 500,000, 1 million miles. The battery is still working perfectly fine. So LFP batteries, the cycling is around 5,000, sometimes 5,000 cycles, which that's a lot. Imagine if you want to charge it once a week, you can run it for a very, very long time. So all of that has become possible because of these control systems and these power electronics. And even after 10, 15, 20 years, when the car is totaled, so most of these cars that you see are running, these electric cars, the battery would outrun the car itself. So probably before the battery goes bad, unless there's an accident or there's other problem, usually the inverter or the motor or the suspension or something else would go wrong. Even after that, the battery still will retain like 60-70% of its peak density, power density. So you can take that battery out. You have a 60 to 100 kilowatt hour battery that's now $500 or $1,000. You can take it out. You could put it in a container and use it as a grid backup system. I helped a friend of mine in the summer actually. He has an off-grid, cabin, and he wanted to, so initially he wanted to buy a Tesla Powerwall, the 10 kilowatt, and they quoted him for 7,000, 6,000, something around 7,000 for that. And that's like 10 kilowatt max peak. So what I did, I helped him. He found a 23 Nissan Leaf in an auction for 4,000 something, and the car was totaled, but it had a clean engine, and the battery was nice and everything. So, and I helped him. I gave him like instruction how to do it, and he was able to use that battery. He's also electrical engineering as well, but you can use that battery, which is now it's a 63 kilowatt hour, so 6 times the size of the Tesla battery, 1/4 of the cost. And he sold the doors and the seats and every part of the car as well. And he technically got the battery and the motor. He still has the motor as well for free. And it's 60 kilowatts, so 6 times the capacity, and it's designed to be on a road, not a stationary battery. So that battery is designed to endure a lot of bumps, and it has a water cool system with the radiator and everything. You just have to take it out, and you could connect the inverter to it and use it as a backup system. So there's a lot of companies, by the way, out there that are using these salvaged cars. They're restoring the battery. Again, the battery may not be useful after 20 years. It has 56. So instead of having 300 miles, now you have 100 miles. Some people don't, still 100 miles you can go on a city trip, but it's still useful if you want to use it in a grid system. Now, it's expected the market for power electronics is expected to grow from 35 billion to 55 billion in 2030. And the estimated growth is 7.74%, 7.74%. So it's a growing market as well. Now, some power electronic systems, you can see the electrical energy, so the graph again, and the components inside of them, usually they consist of a switching device, a linear circuit element, digital circuit, a microprocessor or microcontroller, an electromagnetic device, DSPs, digital signal processing systems, filters, controls, sensors, etc., depending on how sophisticated they are. Some systems would only comprise of a microcontroller and a switch, that's it, and a capacitor, or if you use a rectifier, 4 diodes, capacitor, an inductor, and a resistor, that's it. And a transformer, you may even not need the transformer as well. But some of them, if it's a very sophisticated one, it's going to be much more different. Now, that's the reason if you go on Amazon, and I'm going to show you something, and that's very important. And so if you go, sorry. I just want to show you something. And if you go on Amazon and you search inverter, you can see that my touch system doesn't work. So you can see that this 2000 watt inverter, the one in the middle, one is 197, the other one is 259. Okay, so 2 kilowatt is 259. But if I search pure sine wave 2K, you can see that a 2 kilowatt one or 3000 watt, I will show you, it goes up to a few $1,000s. Now, what is the difference between them? Again, the sophistication of that. So you can see that we have from $100, even there are $50 ones, up to $500, $400, $300 ones. Now the reason for that is because we have different type of inverters. Most inverters that you see, which are car inverters, they are not sine wave inverters. There are AC inverters, but they produce a rectangular AC. Now, for some applications, that's okay. If you want to charge your phone, your laptop, that's okay. But if you want to run a compressor, it's going to destroy your compressor in a week. If you have a fridge, if you have an HVAC, it's going to destroy it. So to have a pure sine, and I'll explain this, it requires multiple steps. Instead of one switch, you may need 10, 20 switches, and it gets much larger, much more sophisticated. That's the reason a house inverter that is grid tied is like $2,000, $3,000, but a same inverter with the same power, it's going to be like $100. So if you see $100, $200 one that is 2K on Amazon, they'll go for it. Usually like very cheap one that are made usually for car. And even a 2000 watt, it's not a real output, you know. It's a rated output, and it usually doesn't get anything near that 2 kilowatt. I would guarantee you if you connect a heater to this, it's gonna just, you know, stop working. Now, so again, depending on the quality of the output signal and the power output, you're gonna have, it may be the same inverter, but you're gonna have different, like it goes from 10 components to 200 components. Now, an ideal switch controls energy flow with no loss. So when on, it has 0 voltage drop and will carry any current. And when it's off, it blocks the flow of current regardless of the voltage. Obviously, we don't have ideal switches. These switches, because they are very high frequency, it's not like a manual switch that you can use like what you have for your lights. These are transistors, MOSFETs, usually FET transistors. And as you remember, we had leakage. So when you, turn off a transistor, you still have a little bit of leakage current going through the transistor. Or if you have turn on a transistor, the transistor has an internal resistance that still drops the voltage. And for a silicon diode, it's like 0.7. If you remember, for a normal diode, the forward bias was 0.7. So you're not going to have an ideal situation. So the desired features of power electronic systems, we want to have 100% efficiency and 100% reliability. Obviously, we can't have them reliability, but still is very good. Most of the cars right now, EVs, they have redundancy. So instead of having one inverter, some of them have two. So if one goes out, there's another one. But the thing is, they have become so reliable right now. I see like 90% of them have one inverter. And the first thing that goes out is usually not the inverter, it's just the motor. And motors are very reliable. So they last a very, very long time. New inverters, the older generations, they were like air-cooled, they had heatsink. Newer ones, some of them even have liquid-cooled inverters. So there is like a type of liquid like oil, non-conductive, goes around the inverter and cools the inverter and the motor. And they have built in a pack, so if you open a Tesla motor, you can see that the inverter is on top of the motor. So it's like a single unit. And obviously they have like a single gear reduction. They don't even have a gearbox. So it's going to be very, very reliable. I think I've mentioned this before. Imagine if internal combustion engine was not popular and wasn't, so prevalent. And someone came to us now, and imagine everyone was driving an EV and said that I have an idea, I want to build a motor, and instead of having one single moving part, it would have 140 to 200. And instead of, being able to charge it at your home, you have to go to a special place to put a liquid in it. That liquid is going to be toxic and it's going to be flammable and it's going to explode. And you're going to have, and can you, make that liquid in your backyard? Obviously, no, you have to dig a well. And you have to change the oil filter, you have to change air filters. And the whole car, instead of having 2,000 parts, it's going to have 14 to 23,000 parts. So it's a lot of moving parts. You have to change all those moving parts. And you will go like, what the reason? It's going to be, electric cars are going to be much more efficient. So normal electric car efficiency is 95%. Best F1 Formula One that use high compression, that's at around 40% maximum, something like that. 60% is lost during heat. Generates a lot of heat. You need to have a gas tank. You need to have exhaust. It's a lot of, if they were able to figure out the battery problem, it's not going to be a no-brainer. You have bullet trains that go 400 miles an hour, 300 miles an hour. No, diesel train is going to come anything close to that. So the efficiency is going to be very, very high in power electronics, and it's going to be much, much more convenient that whatever we already have. And reliability, again, is going to be much higher as well. They're going to get, from now on, it's just getting better and better, reliability and everything. So just this last slide about the power converters. So switches, we want them to be powerful, efficient, and reliable. Reliability is almost there. Efficiency, it could get even better. Now it's 95%. You have nothing close to that. No other type of energy conversion is close to that, but could even get better than that as well. Now, the problem is with these systems is power density, and it's not from the electronics and the motors, and it's the power density of the batteries. So if the battery power density could double, it's going to solve a lot of problems. Now, then one of the main parts in a power electronics system is a power converter. A converter is a general term for an AC to DC converter that is shown above. It's a general term that means we are converting one form of, the signal to another. Converter are usually used for DC to AC to DC. For DC to AC, we usually use the term inverter. Okay, so if you use a converter, it usually means AC to DC, and usually means rectifier. So in general, converter, most times if you heard that, it's rectifier, and inverter is type of converter, but we usually, when we say inverter, it's a DC to AC. So we have two types of converters. We have rectifier mode of operation when power goes from AC to DC, and inverter mode when it goes from DC to AC. Another type of converter that we have is from AC to AC, and another one is a DC to DC, which we call buck or boost converters. And as mentioned, they can also convert DC to DC and AC to AC. Now, practical switching devices are selected based on their power handling ratings, the product of their voltage and current ratings, rather than their power dissipation ratings. And I'll explain more about that in the next class. It seems that we are out of time. Thank you so much. If you have any questions, again, just please email me or call me. I'll post the videos online, and I'll see you on Wednesday. Thank you.